18.3, we're going to be talking about salt hydrolysis. What occurs within a neutralization reaction? You have your parent base, and this is in no particular order, but you have your parent base and you have your parent acid, and when they react through a neutralization reaction, you get your salt from the metal of your base and the anion from the acid, and then you also get water from the hydroxide of the base and the hydrogen from the acid, hence neutralization. However, this is a very loose term of neutralization because it does not necessarily make a neutral solution. It really depends on how the ions in which are being formed react with water. And then that can cause hydrolysis, what we had talked about back in 18.1, of water also dissociating within the solution, creating hydrogen ions and hydroxide ions. Therefore, salts can push this forward sometimes as well. First, we're going to look at anion hydrolysis. So A-, the anion, is the conjugate base for the parent acid. If you have a weak acid, you are going to have a strong conjugate base. That will cause you to hydrolyze water. If you have a strong acid, you're going to have a weak conjugate base, and that does not hydrolyze water. So it's the vice versa situation. What this looks like is you have your conjugate base, so your anion, that is going to interact with water, causing water to dissociate back into that parent acid, and then we're going to make a hydroxide ion as well, therefore changing the pH of the solutions. Because we're adding hydroxide is a base, therefore we expect that pH value to increase. All right, so cation hydrolysis. Looking at the positive. So M positive, which is the metal, is the conjugate acid for the parent base. We're focusing on the nonmetal here. We have our nonmetal, like sodium, that could react with water, which would then cause to remake that parent base and release hydroxide ion, or hydrogen ions, sorry. And when we release hydrogen ions, your pH value is going to decrease or get lower. You're going to make a more acidic situation. And this again is going to occur in the same way in which you have the base is weak. So this is a weak base. So you have a strong conjugate acid, and therefore you're going to hydrolyze water. If you have a strong base, you have a weak conjugate acid, therefore it's not going to hydrolyze. However, there's another situation that can occur with cation hydrolysis that makes cations a little bit more difficult in which to predict and work with. So that metal ion, the outcome will depend on its charge density, that of a small ion with a +2 or +3 charge. A charge density is comparing the charge and the ion size of the atom in which we are looking at, which is why we need a +2 or +3 charge, a relatively high charge, and a small radius on that atom. What that allows for, using an example, is here we have aluminum. Aluminum carries a +3 charge. When aluminum is the metal ion that we're looking at in the solution, it is going to create a lot of dative bonds with that water. However, because of how much is going on with this water, there's a lot of interaction occurring. And when you get too much of this interaction occurring, you're going to break at least one of those OH bonds. So when that happens, you create the same kind of structure with aluminum surrounded by all its waters, but one of those waters has lost a hydrogen ion, and mostly for space. And what occurs here then is then you have this +3 charge of aluminum, but you have a -1 charge on that one water, which is now a hydroxide, and that released a proton into the system, which will cause the pH to decrease. Down below I have the chemical formula written. So aluminum with 6 waters has a +3 charge in its complex ion form. When you have too many waters around one atom, one or multiple hydrogens can break off. And so here's how we represent that new complex ion. Aluminum with 5 waters with an OH releasing a hydrogen ion. This typically will occur with beryllium that has a +2 charge, aluminum with a +3 charge, and transition metals, but most notably iron with a +3 charge. So high concentration of positive ions causes the electron density to be attracted from those OHs, and this is what causes the hydrolysis. More than one water can be hydrolyzed, and here are those metals again in which you can react with. All of the salt hydrolysis can be deduced by the strength of the parent acid or base, so you can determine if the neutralization reaction will actually be neutral, basic, or acidic. What does that look like? All right, so if we have a strong acid and a strong base, we react the two, like HCl and NaOH. You get a salt, like NaCl. Because it's a strong acid and a strong base, and NaCl is just pure salt. It's not tied to a weak acid or a weak base. You do not get any hydrolysis. Therefore, you are neutral with a pH of 7. If you have a weak acid and a strong base, like acetic acid, CH3, COOH, and NaOH, you will get a salt of the conjugate base of that strong base with that weak acid. This causes anion hydrolysis. When you have anion hydrolysis, you're going to be absorbing more hydrogen ions and releasing hydroxide ions. Therefore, you're going to be basic, and your pH value is going to be above 7. Vice versa, if you have a strong acid and a weak base, like hydrochloric acid and NH3, you're going to make the salt NH4Cl. The way in which this one works is you're going to get a cation hydrolysis, and therefore you're going to be absorbing more of the hydroxide ions of the water, releasing your hydrogen ions, creating an acidic solution. The last one is if you have a weak acid and a weak base. This one, if we use CH3, COOH, and NH3, here's your salt, NH4, CH3, COO. You do get an anion and cation hydrolysis. However, this is a little bit more unknown. You'd have to run a titration in order to determine this, because it depends on the relative strengths of these conjugates in which are being created. Therefore, we cannot determine it. Then, what we do need to know, essentially, is the relationship of the strong acid, strong base, weak acid, strong base, strong acid, weak base, and their effects in determining is pH actually going to be affected by the neutralization reaction and not actually be at 7.